Hello and welcome. After the successful division function, I tried to increase the clock frequency of the system. And here in this picture here, you see the 4 different clock signals of the relay CPU. The relay CPU not only has one clock signal, no, we need 4 different clock signals and a little break between two clocks for the system. And the reason why we need this is because in my system, a register has to be deleted before we can rewrite it. Here you see a picture of a register. And a register is storing the information by a relay which is holding itself. So if this relay is storing a 1, this switch here is in this position, and with this 24 volt here and this position, the relay is holding itself. And if we want to store a 0 in this bit, we have to delete the register and then we can store a new information. And because of this, we have to delete all registers before we can write them. And this is done during clock 0. Clock 0, clock 1, clock 2, and clock 3 are one cycle. And for example, an operation command, which you see here, consists of 2 of these cycles. In the first cycle, the address bus register is written and the program counter help register is written. In the second cycle, we write the new opcode of the next command into the instruction register. And this timing is controlled by a module of the control system of the CPU, and it is this module here. This is the control line timing module. If we want to send an input enable signal to a register, this module is responsible for sending a clear signal to this register during clock 0. In clock 1, we will send an input enable to all registers which should be written during this cycle. Clock 2 and clock 3 are only necessary for this step registers here. We have different steps for each command. The operation command consists of 2 steps. Some of the more complex commands consists of up to 8 steps. And here you see the timing of the cycle during the division video. And we have 10 milliseconds for clock 0, then 5 milliseconds break, 20 milliseconds for clock 1, and so on. And in summary, here you see a picture of the logic analyzer. We have 70 milliseconds for one cycle. That's a lot. And then I tried to reduce this timing here. And this was the result. This was the timing I tried in the video this follows now. From 8 milliseconds, then 4 milliseconds break, then only 50 milliseconds, 4 milliseconds break, 5 and 8. In summary, 52 milliseconds. I reduced it from 70 milliseconds to 52 milliseconds. And the very interesting result was that the complete program ran without any problem. There were no crash of the system. The state machine was working properly. The complete program was finished, but, and this was the interesting part, the calculation result was wrong. And that was funny. And then I tried to analyze what happened here. How can it happen that the program is running without any problem, but the end result is wrong? And the reason, I'm not 100% sure, but I think that is the reason. The reason is the result register here and the arithmetic logic unit here where the adder is located. And the interesting thing now is that if we start with a new cycle, if we start to add information coming from the data bus to the accumulator, this is done in the ALU. And the adder starts its work here. And here you see a part of the adder. And the problem is the last relay on this side here, this relay number 3. Because when we start with a new cycle, during this clock 0, we delete the result register. Then we have a little break, 4 milliseconds. So we have 12 milliseconds, and then the input enable here is active. The input enable of the result register is active at this point. But at this point, relay number 3 may still not be active. So we have 24 volts here, maybe to the output. If this relay is open, then is closed, then we have the 24 relay to the output. So maybe each relay needs 5 milliseconds. 5 milliseconds after start the first relay, then 5 milliseconds the second relay, and then maybe 5 milliseconds the third relay. And after 50 milliseconds, the 24 volts high are going to low. But after 12 milliseconds, the input enable of the result register is active. So we are storing a 1, but we should store a 0. But the 1 is still active when the input enable of the result register is active. So 12 milliseconds are too fast for the 50 millisecond chain we have here. And I am 95% sure that this is the reason why in the following short video the division function is not crashing, but we have the wrong result in the accumulator after the function. And I completely underestimated how important it is to have enough time during clock 0, because I thought that this clock 1 is the most important where we should do the work, but that's not correct. The most important clock is clock 0, because in clock 0 the, I would say, work should be done, and clock 1, we only need 8 milliseconds to be sure that we can store the information calculated during clock 0 in the registers. And now, in the following video, you see the wrong calculation of a division function without a crash.